In Haskell, when you're dealing with records, then sometimes you do not just want to represent the values of a particular record type, but also variants of this value. So, for example, partial values or annotated values. And there is a common design pattern for that, which involves just abstracting over a type constructor and then parameterizing all the fields of the record by that type constructor. And this design pattern is sometimes referred to as hierarchy-kinded data types. And so in this episode, we want to look at this pattern, a couple of examples, see what the implications are, and discuss it.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions and comments in the chat, and we will try to show them on screen and discuss them.
Yes, okay, so to start, I have entered here an example record type, which is like episodes. You can think of it as episodes of this show. So we have a record with 4 fields, an episode number, which is an integer, a title, which is text, an abstract, which is text, and sort of a difficulty level. Don't take that too seriously. It's just I have 3 choices here: beginner, intermediate, and advanced. And then I have a slightly erroneous record for this episode, which says that this is episode 14 with a wrong title, a partial abstract, and a preliminary level. So it could be that we discover this error and that we have some kind of application where we can update values and we want to make changes and we want to represent sort of a partial update of this record, where we would like to say something like ep14 update, right? And then we don't quite know what type, and we would like to either ignore or do something where we basically say make episode ignore the first thing, say higher kind of types here. Ignore
kind of like higher
yeah,
it's a good name.
Okay. And perhaps also say that, I mean, again, that the level is perhaps more like intermediate than beginner or something like that. But I mean, if we don't have all the values, we would really like to have maybe in every position, right? So maybe int, maybe text, maybe level. But we can't do that with the same type definition. We can make a separate type, but then they're completely different, unrelated. There is a different constructor name. And but if we want to keep this relationship precise, then one option that we have is to simply add an extra argument here, an f, and then wrap every field in an application of f, and then go from there, right? And now I'll first comment out this, because before we can get back to our update, we first have to clean up everything that is going wrong now, right? Obviously, episode 14, as it was originally written, is no longer entirely correct, because first of all, our type now needs an argument. And if we want the original type back, then we have to instantiate f to essentially the identity function, right? The identity function is not really in existence on the type level, but we have something in data.functor.identity, which is in base, which looks like this. So it's a new type with an argument, and it has a constructor which is also called identity. So if we use identity as f, right, then we get identity of int, identity of text, identity of text, identity of level, and every identity thing contains just an a. So that is morally the same thing as we originally had. It just makes everything slightly less nice looking, right? And there is a bit to say about this, but I don't want to go into too much detail in this episode. I think so some libraries, some places where this is being used are using particular tricks, using type families that, like special case, something like the identity, and then make it so that you don't actually have to write the constructors in these cases. but that comes at a price, right? It makes everything less regular, and there is this hidden type family that makes like reasoning about the whole thing more complicated. So in general, I'm not a huge fan of this approach, but in particular in this episode, I don't want to do it because I want everything to be relatively straightforward and clear. Right. One could also use a shorter name here than identity, but like again, we're just keeping it like this. The second mistake we're seeing is that now we cannot just derive show for a type like this. Unfortunately, GHC is currently not clever enough. And again, there are some tricks one can play to still derive a relatively general show instance here. But again, I don't really want to go into that in this episode and just do something simple. So I'm going to use standalone deriving, and I'm simply going to derive a show instance for the special case where f is the identity. And then we can still like show the value f14 if we want.
It's
right?
perhaps worth pointing out that a more general way to define a show instance is using quantified constraints, which is, and we have a separate episode all about quantified constraints. So if you're interested in that, you might want to look at that one instead. Or in addition.
My LSP does not want to evaluate f14. I can briefly try to restart and see. Okay. The evaluation plugin is sometimes a little bit
it's not very
unstable, but so now I can show this, right? And now we can go back to our update, and we can actually instantiate the f here to maybe. Our type constructor becomes maybe, and then everything in here, this becomes nothing, and this becomes nothing. This gets just, and this gets just. And this gives me a way now to really talk about such a partial value, right? And another thing I could be doing is to start out with sort of an empty episode where everything is nothing. So all 4 fields are nothing. And then I could also write episode 14 update as empty episode where I just take the title and set that one to just higher kind of types, and take the level and set that one to just intermediate. Right? I mean, there are many options here. Okay.
Mm-hmm.
And now, of course, I might also want to actually implement something like this update, right? Update episode could be, if I have an episode, somehow episode and empty are too close together. If I have an episode of type episode identity, and I have a partial episode maybe, I should be able to combine them into a new episode where I'm basically using every piece of new information that I have obtained from here to override what I had before, and everything where I don't have new information, I keep using the old one. And this one is easy enough to implement, but one of the nice aspects of this general pattern is that types that are defined like this, where you have like a record and every field is wrapped in a type constructor, they adhere to some common structure, and that structure is reminiscent of that of an applicative functor, only that it is an applicative functor that is also used at higher kinds, right? I mean, so like, by the way, I mean, sort of the name higher kind of types or higher kind of data types comes from the fact, right, that we are parameterizing here over a type constructor, and the f is of type to type in this case, right? And then our episode type, so the types that we are talking about, have this kind, right? Type to type to type. So these are higher kinds, but of course, perhaps not an ideal name, because there are many other higher kinded types as well that don't necessarily fit this pattern. So let's briefly look back at applicative functors. So the normal applicative class is as a superclass and has two methods: pure, which is of a to f of a, and has the star operator, which is f to a b to f a to f b. And we want to do something similar here. We want to define something which I'm going to call h applicative here, for a higher order applicative, if you like. And we have an h pure, which replaces pure. And that is supposed to go to some h type, which is parameterized over an arbitrary f. And we need something with f here, but we still have to talk about what exactly. Right, and then we have some replacement for the star operator, which I'm just going to call h-app. And this is going to go from something like f, kind of g, f to g, but this doesn't quite work because f and g are themselves type constructors, right? Like things like maybe or identity, and we cannot just have a function from identity to identity or maybe to maybe. That is not kind correct. So we need to talk about this. And then we would like to go from an h of f to an h of g. Okay.
Mm-hmm.
And as an inspiration for what we would like to express using h pure, we have this empty episode value, right? So this is really something we want to make. We want to define an instance in the end, h applicative of episode, where h pure can be used to define something like this, where every field is the same thing. Now, the interesting aspect is that we have different types that f is being applied to. Right, so in order to be able to use a value such as nothing in all these places, why does nothing work? Well, because the type of nothing is polymorphic. If you look at the type of nothing, it is maybe a, or if we spell out the for all, it's for all a, maybe a. Right, so it's a polymorphic type in the maybe constructor, and because it's polymorphic, we can in particular use it as a maybe int and a maybe text and a maybe level as we need it here. And this turns out to be actually what is required here. So we want something which is for all a, f of a. And this is a so-called rank 2 polymorphic type. And it means that the caller of the function has to supply a value here as this argument that is itself sufficiently polymorphic, right? When we did the episode about parametricity recently, we talked about sort of the different roles of an implementer of a function and the user of a function. And typically polymorphic types, they restrict the implementer because the implementer cannot really make any assumptions about what a polymorphic variable is. And the user has freedom. The user can choose something. Here, the roles are basically flipped. If we use a rank 2 polymorphic type, the roles get flipped. The implementer has more freedom again, because we get a polymorphic function. We can use it for an arbitrary instantiation of A. But the caller of the function is more restricted. They have to supply something that actually is sufficiently polymorphic. So let's try this. So let's try to write pure episode now, which is of type for all a, f of a, episode f. And pure episode takes this sufficiently polymorphic value, let's just call it x, and creates an episode by putting x in all these 4 places. And this type checks. And now we can actually write empty episode as pure episode applied to nothing, because nothing is sufficiently polymorphic. Okay. And so for app, the idea is that well, we have a structure of functions, right, and a structure of arguments, and we want to apply the functions to the arguments. We basically want to do the same thing here. But as I said, we cannot just have a function f to g, because f and g have the wrong kind. We have to do something like for an f of something to a g of something. But if you look at the episode type once again, and we would want to change the f to g in all these positions, the arguments stay the same everywhere. So we need to be able to map an f of int to a g of int. We need to map an f of text to a g of text, and we need to be able to map an f of level to g of level. So again, we can do this by essentially being polymorphic. So we want something which is essentially going for all a, f of a to g of a, right? But because here we expect something which is itself a type constructor, we can help ourselves again by doing a definition via a newtype, where we define some sort of fancy function arrow, which is parameterized over an a. And we can invent a constructor name, and we can invent a selector, and we can go from f of a to g of a. Okay. Getting errors because this is actually already defined down here, which I can now remove. And so if we have this, right now I can define app episode, which goes from episode of f arrow g to episode f to episode g. And here I just get an episode which has 4 functions, and I get an episode which has 4 arguments. And basically, just as I said, I want to apply all the functions to all the arguments, but because my functions are wrapped in these newtype constructors, I need to extract them using apply. So I need to actually write apply f1 x1 rather than just f1 apply to x1.
So just one clarification. Anders said earlier that it's like a for all, but we basically have 4 functions, each of which has potentially a different type, right? So we have an f of int to a g of int, we have an f of text to a g of text, and we have f of level to a g of level. So in that sense, it's a little bit different from what we have to h pure. There's not a rank 2 type.
That's true. That's true. Yeah.
So I guess we have a definition of h applicative now.
Yes, exactly. So we can complete the definition now. So actually, if I go down here, I have written the class. I should be able to define an instance now, h applicative of episode, where h pure is pure episode, I think I called it, and h app episode, and that part checks.
So at this point, maybe there's a question here that might be useful to consider. Yeah. So this person asks, goes by fundamentals, what laws of applicative are we most interested in here? Which is an interesting question.
Yeah, that's an interesting question. I think it's not, I mean, it is always also about the laws, but it is primarily about the generality, right? So, I mean, so the goal, if you remember, was to write something like update episode. And what we now can actually do is we can write update episode as a much more general function. We don't even have to write update episode. I can just write update, and I can define this function completely in terms of this h applicative interface. So I can write this as h identity to h maybe to h identity for everything that satisfies this h applicative class. And that is a huge advantage, right? Because, I mean, there are many different record types of this shape that I could define, right, in one application even. And I immediately, by making them an instance of h applicative, I have this update function for all of them. And that is just one example, right? By having this h applicative interface, there are many operations involving various different instantiations of f that I can essentially generically write over all these kinds of record types and then get them for free. And of course, there is, like, I mean, there are certain laws that we have for applicatives that also like basically extend to H applicatives or are supposed to extend to H applicatives. But I think the main power we're gaining here is just one of generality, right? That we don't have to reinvent functions for all the different record types, that we can just write once and for all.
But for example, one might imagine that it would be nice to be able to say, like, if we have this very general update function that Anders was showing at the bottom here, which we have yet to define, but we might imagine that perhaps, hopefully, with the laws that even if we don't spell them out right now, we might be able to prove that if we apply the empty update, we get that's the identity function, right? So there are certainly definitely useful things that we could say there.
Yeah, that's true.
And there's another question that perhaps might be useful to consider before we look at the definition of update.
Sure.
So this is a question, I think, about the difference between hpure and hup, going back to my comment about one is universal, one isn't. Why do we have a new type for the function thing, and why don't we have a new type for the argument of hpure? And like my answer would be is because maybe you have a different opinion here, but my answer is that for the hup, for every argument A, like for every type A that we have in the record, like int, level, text, we want a function from f that thing to g that thing, right? So we need a type level function that expresses precisely that, right? That's what this new type is. We just don't need that for hpure because we're not applying something to every type in the record. It's like in that case, it truly is for all A and f of A.
Yeah. I mean, at least that is sufficient, right? I mean, in principle, one could say for hpure that is not strictly, I mean, for an H applicative as a class, it would be very difficult. But for episode, it would in principle be sufficient if we have an f that works for int, text, and level for these three types. And there are sometimes variations possible, right? But this is sufficient here, and it's a good choice. In general, there is an observation that if you move to parameterization of data types over type constructors, like if you have data types like episode, which are parameterized over something that is itself of kind type to type, like we have here, then very often you get rank 2 types in the functions that operate over this. Like there is a sort of a natural correspondence between like abstracting over higher kinds and getting types that have higher rank, but it leads too far to explore that.
Perhaps a different episode.
Yeah.
I have one simple question for you. Which language extensions do we need to do all this?
I mean, at the moment, I have overloaded strings here, but that is just for text, and I have GADTs, but that is for something else. So at the moment, this is all in GAC 2021, I have to say. Let me briefly think. I mean, so if you assume Haskell 2010, then this sort of stuff needs rank n types as a language extension. And I don't think any of the other things that we've done uses any language extension. So compared to Haskell 2010, I think it's only rank n type so far.
Yeah.
Okay. So yeah, I mean, I want to actually define update. So it's not too difficult, but the idea is that so basically, if you use normal applicatives, right? The cool thing about them is often that you can essentially apply a function within a context to multiple arguments by doing a construction like pure f, where f is now some function, and then you use the star operator to supply all the arguments, right? Something like this as a chain. If f is a function with 3 arguments, you can write something like this. And here we can do the same thing. We basically have 2 things that are in this H context, and we can supply them both using happ, like just as we do with the star. So we have our original value and our new value, our new partial value, and we can supply them here. And in the beginning, we have some H pure of something, right? And basically, this chain now dictates what we have to put here. And this looks slightly more difficult than it needs to because of these fancy arrows, and they are not infix. But essentially, we need a sort of a curried higher function from identity A to maybe A to identity A. Right? So that is what we really need. And so let's actually define this. Like, we need something like from identity A to maybe A to identity A. Okay. And if we look at this even more closely, right, I mean, we could also say what we really need is, I mean, because identity is more or less the same as A, it's primarily something of this shape, right? And then we need to wrap and unwrap new type constructors in the right way. All the rest is just unwrapping and unwrapping new type constructors. And this function that we want here is simply one that says, well, we have our old value, and if the new value is nothing, then we want to keep our old value. And if we have an old value and we have a new value, we want to use the new value. That is the function that we want to do. And now if I look again and I see what I actually need to put into this place, right? I need to put something here that is not this strange arrow. So I need to go from A to maybe A to A to what I actually need here is identity fancy arrow maybe fancy arrow identity of A. And because all this is just new type wrappings and unwrappings, I should actually be able to just say coerce here. So coerce is not in scope, so I should bring that in. So that's save new type coercions, and basically if I write convert of augs here, that should be fine.
Yeah, just to point out that this is safe coerce, right? This is not this is checked by the type checker.
Yeah, I mean, I could unwrap and wrap the new type constructors myself, but this is appealing, right? And now I have my update function. I can also try it out. I can see if this actually works. If I can call update on my app14 with app14 update, I think I called it, and see if this works. And I get my episode back, which is number 14, higher kind of types, and the level is intermediate. Okay. All right. So in the final minutes, I wanted to briefly sketch some application where this is actually put to good use. And one area where this sort of pattern is put to good use is various database libraries. I mean, there's also libraries such as Barbies, which are basically giving you support for this pattern in particular. And there are other libraries like large records or large anonymous records and SOP, which are also using this parameterization by a type constructor. So this all exists, but in particular in some database libraries like Beam and Relate, this is really being used as the pattern for your table type. So if you have a database and episodes exist in your database as a table, then in Beam and Relate, you would define a Haskell data type like this for that table. And why is this nice? Because you cannot just use this data type now to refer to the values that come from that table, to the actual rows that come from that table, but you can also use it to associate meta information with the table, such as what names are being stored in the database, and you can use it to build expressions, like query expressions for these tables. So yeah, let me just very briefly sketch that. So we could imagine that we have a table schema type which is parameterized by a type such as expression, and the table schema type episode, yes, such as episode. A table schema type could contain a name which is sort of the name of the table in the database, and the names of the columns. And the names of the columns, we need a name for every column, for every field here, but they are all strings. So we can use as a type constructor something that maps any type to a string. And there is another type constructor just like identity for this, which is called const. So we can, I just have to find the right spot again, sorry. We can use something here that is an age applied to const string. And then we could define an episode schema, which is a table schema for episodes, which is a table schema where the name is, let's just say it's episode, that our table is called episode. And our names of the columns are, let's also just use more or less the normal names. Let's say perhaps the number is called NR, and the title is called title, and the abstract is called abstract, and the level is called level, right? And so our database system could now use these names. And if you look, for example, at Relate, that this is sort of a simplified version of how it's being done in Relate, then you'll find something which is much like this, and Relate uses this. And then just to look at an example query, how a query could look like. Query you can think of as a monad. And so you have a do expression. And so you can use something like this episode schema that we just defined to select every episode. And then you can use a guarded clause. And then you can use like a field extraction from the episode to compare with, say, with a literal expression of type integer, to say, I only want the episodes that have a number that is less than or equal to 3. But here we are operating sort of on a symbolic episode within a query, like the name, we assign a name to the episode, and we select a field from that. This is like a variable name, right? And in the actual query, this would end up as a variable name. And that is expressed using this expr instantiation. And then in the end, we just return all these episodes. And I don't really have the time left to show this, but I mean, I have a very simplified implementation of like something which is inspired by Relate. And again, Beam is not much different down here. So let's just try to see if I can make this work. So if you have a query like this, you should be able to say something like render query. And again, this is very primitive to get some very simple representation of the query, right? So you can see that we're selecting everything from the episode table where the number is equal to 3. And this is using these names that I have been putting here, right? So the number is now called NR because we've said that the name of that field is using NR. And if I actually run this against the database connection, let's see, then I'm actually getting the first 3 episodes of the Haskell Unfolder with their descriptions, right? And this is
one thing that's
yeah. Go ahead.
It's worth pointing out, I think, here is that the on line 180, right? That number episode, that number is the regular old selector, right, for the record. And the interesting thing here is that it's a expression, but it's a variable of the right type. It's an int, right? That's why we can compare it to 3, right? So it's the the const string for the names that sort of ignores the type information, right? It's metadata that doesn't care about the type, just a string, right? But these variables, they're not values, right? They're not like 3 or 4, but they are typed, right? It's a variable of type int, therefore we can compare it to an int. And so we really are making use of the structure of the record there too. Which I think is very nice.
Okay. Yes. I think I hope I could demonstrate that this is useful. So are there any more questions?
We have one final question. Since you started talking about records, we should have expected this one.
Would this work as episode.number with overloaded record syntax too? Yeah, I see absolutely no reason why not. I mean, do it overloaded record of, and then go back to number episode. rerun here. Yeah, still works. I mean,
Hooray, we have real records.
yeah.
I don't think we have any other questions.
Okay, then let's go.
All right, so thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And feel free to leave any comments below. We'll leave the stream open for a few more minutes if you want to ask questions. And otherwise, feel free to just put them in the comments below and we'll try to answer them asynchronously. And hope to see you all in 2 weeks.
Yeah, thank you.